Hi everyone, I am Priyanka and I will be covering the theory behind this paper, specifically how entangled photons are created through the process called spontaneous parametric time conversion, that is SPDC, and the mathematical framework of Smith decomposition that makes the phase sensitive imaging possible. So, picking up from where Reva left, we now know the phase problem, that is, when we shine X-ray on a crystal and measure the diffraction pattern, we get the measured signal that is proportional to the modulus square of the Fourier transform of the charge density. With this, the phase of the charge density is lost, and without phase, we cannot reconstruct the real space structure of the sample directly. So the question is, how does quantum mechanics solves this? The answer is entangled photon. So in next few minutes, I will cover four things. That is how entangled photon pairs are created. Second, the quantum state of the entangled photon pair. Third, the schematic decomposition of that state. And finally, the schematic number which quantify how entangled the pair is. So, how entangled photons are created? The key ingredient in this experiment is nonlinear crystal, one with the second order susceptibility, that is Chi2. When a pump laser enters this crystal, it spontaneously splits into two lower energy pairs or photons, that is signal and idler, and this process is called SPDC. Now, I want to emphasize the word spontaneous means there is no seed field or no stimulation from outside. This splitting is purely because of quantum vacuum fluctuation, and that is why the output photons have quantum correlated that no classical light source can reproduce. Now, this signal and idler are subjected to the conservation law. First, the energy conservation, that is the pump frequency. The pump frequency is equals to the sum of signal frequency and the idler frequency. The second is the momentum conservation, that is momentum wave vector is equals to the signal wave vector plus the idler wave vector. From this, we can say that the signal and idler momentum and the energy are not independent, they are correlated. Like if we measure the signal's energy or momentum, we instantly know the idler's energy or momentum or vice versa. This correlation between these two photons enforced by the conservation law, which is we call the entanglement. So now let us make this mathematical precise, and this Chi2 nonlinear interaction Hamiltonian for SPDC is written in equation 1, and we treat the pump laser as a classical field, and the signal and idler remain as the quantum field operator. Here this EP and AP represents this spatial amplitude profile, and the exponential term include the spatial phase term and the angular frequency term. So by substituting this mode expansion of E minus, which carry the creation operator, that is A dagger, and we get this equation 2. You notice that the two creation operators, that is A dagger Ks mu s and A dagger Ki mu I, appears together, and this is SPDC interaction that create one signal photon and one idler photon simultaneously from the vacuum. Now we apply the first order time independent perturbation theory. We start from the vacuum state, that is written, which is written as get 0s and 0i, and the state evolves as phi get phi, which is equals to the vacuum part minus the integral of the Hamiltonian acting on vacuum. And when this Hamiltonian interaction Hamiltonian act on the vacuum, the Hermitian conjugate terms, which contain the annihilation operator, gives a zero. This means that only the this AS dagger and AI dagger terms survive, which create helps in creating this 1s, ket 1s, and ket 1i. So the perturbation expansion contain two integral that we need to evaluate. First is the spatial integral over the crystal volume, and it produces a gamma function, that is gamma of Qs plus Qi, and which is the Fourier transform of the pump beam transverse profile. Second is the time integral, and this equation 5 gives the delta function, and it enforces the energy conservation. Now combining both equation 4 and equation 5 and absorbing all the constants into the prefactor and defining the two photon state of the entangled pair, which is given by equation 6, that is ket psi. And this is the state of the entangled pair, which is the sum of all overall allowed momentum pairs weighted by phi, ks, and ki. And this ks and ki cannot be factored as f of ks times g of ki, because the conservation law couples the two momentum together. Thus, the photons are quantum entangled. Now, we evaluate the two photon amplitude explicitly. To do this, we will use this paraxial approximation. This means that the light beam travel mostly in forward direction with only small sideway spread. In this limit, the full wave vector splits as k is equals to q and kz, where kz is given by this. Now the transverse and longitudinal part of the spatial integral separate, and we can evaluate each one independently. The transverse part integral over the pump beam profile and gives a gamma function, which is the Fourier transform of the pump's transverse shape. And for the Gaussian beam with the width sigma p, this is the Gaussian in ks and ki, ks plus ki. And the longitudinal integrate over the crystal length Lz, which gives the sinc function, and the phase mismatch, that is delta kz, depends on ks minus ki, and the integrating over the crystal gives Lz. That is this equation 12, where L square is defined as Lz lambda p by 4 pi, where Lz is the length of the crystal and lambda p is the wavelength of the pump photon. Now multiplying the transverse and longitudinal contribution, we arrive at the equation 13, and this equation 13 has this gamma factor that controls the sum of the momentum, enforcing the momentum contribution, and the sinc function controls the difference or enforcing the crystal phase matching. Together, they determine which idler or signal momentum pairs are allowed. And equation 15, you can see here, is the complete or the full state field, including the vacuum state, which represent that no down conversion happens That is why the SPDC is a rare process that is proportional to the Chi2 medium. Now we come across the most powerful mathematical tool in the paper is the schematic decomposition. Think of it as a quantum analog of singular valued decomposition, but for the joint wave function of two photons. The schematic decomposition theorem states that any square integrable function, that is phi, qs, and qi, of the two variables can be written as the sum of separable terms. To find these terms, we first construct the signal reduced density matrix by tracing out the idler or integrating over the idler degree of freedom. And this gives equation 16. And it has the set of non-negative eigenvalue, that is lambda n, and the orthonormal wave function mu and q. Similarly, we can define the idler reduced density matrix, and the same lambda n also appears in the idler reduced density matrix with corresponding eigenvectors, that is v and q. This is guaranteed by the singular value decomposition theory. So now come to the reconstruction of the amplitude part. So we expand this phi in the UN basis. Using the orthonormality of UN, we can extract the coefficient of each terms. Substituting back the signal density matrix and matching with the eigenvalues equation forces the coefficient to be the square root of lambda n Vn. And the equation 13 is the amplitude of two photon, which is written in the separable terms of Un and Vn. And this weight lambda n tells you how much each mode pair contributes. And if lambda 0 is equals to 1, then there is no entanglement occur. And if many lambda n are strongly or equals to many mode contribution, then the entanglement has very strong possibility. Now we want a schematic number that captures how entangled the state is by defining the term kappa, which is inversely proportional to the summation over lambda n squared. And to get a closed expression of kappa, we make one approximation by replacing the sinc function with the Gaussian pump. The amplitude becomes the double, our amplitude becomes the double of the Gaussian, that is Qs plus Qi and Qs minus Qi. Now we will change the variables as like let Q is equals to Qs plus Qi divided by root 2 and P is equals to Qs minus Qi divided by root 2, and substituting this in the previous equation, and we will get as phi q p, and we will obtain this new coordinate where this phi separates this q and p terms, where a and b, like a and b is defined as sigma p and b is defined as 1 by 2l. And this separability is the key step. It is what allowed us to compute the schematic eigenvalue analytically. For 1D double Gaussian, the schematic eigenvalue is given by the geometric series of lambda n is equals to 1 by r squared dot r to n, where r is defined by a minus b by a plus b. Now computing this k from this series, which gives us the kappa is equals to a square plus b square by 2ab. But our problem is two dimension. So the transverse plane has both x and y. Since there are two dimension are that is independent and identical, the 2D schemate number is the square of the 1D value, like 1D k value. So we will square the previous term and we obtain that kappa, that is the schemate number, is equals to a plus b whole square divided by 4ab. And we will substitute the values of a and b from here, and we obtain this final expression as kappa is equals to 1 by 4 bracket sigma p l plus 1 by sigma l whole square. So the figure you are seeing here is the plot between the schemate number and versus the pump crystal parameter. So you can see the minimum value, that is k is equals to 1, occurs at sigma p l is equals to 1, which is the case of a separable, and the two Gaussian width are equal, that is r is equals to 0 and lambda 0 is equals to 1, and the photons are not entangled. But as this sigma pl moves away from 1 in either direction, kappa grows rapidly, signaling a stronger and stronger entanglement. So now, like we numerically generate and visualize the biphoton intensity distribution as the stack content plot with different schemate number within the Python code. So let me show you my Python code. Wait a minute. So yeah. So here, what I did is like I created this 2D grid points. You can see. Then I define my row S and row I as the axis of plotting, and then I compute this phi using the exponential under the Gaussian approximation, and which returns this phi square, which is basically my intensity. And I set my parameters that is same as shown in the paper. And then I created this 3D plot and having this vertical space between the layers. And I created this for loop for the case, and finally compute the intensity and normalized it so that the plots are comparable. So let me run this code. So here you can see 5 panels. It is 1, 2, 3, 4, 5. So 5 panels you can see. At kappa 3 is equals to 1. That is the middle one. The amplitude is round Gaussian block, and these photons are separable. That is not entangled. So as we move downward, which is K1 is equals to 2500, and the distribution collapses into a very narrow ridge along the diagonal, that is rho S is equals to rho I, and the photon position are perfectly correlated. And similarly, when we move upward, that is K kappa 5 is equals to 2500, the ridge is along the anti-diagonal, that is rho s is equals to minus of rho I, which are in anti-correlated position. And our let me go back to my slides. Hmm. So our reproduce figure that matches exactly with the paper figure very closely, and the kappa value and the transition from the Gaussian block to the ridge as entangled increases are correctly reproduced. So at last I can summarize all the discussion that I explained is that first of all, we derived the two photon state from SPDC Hamiltonian using the first order perturbation theory, and then we obtained the biphoton amplitude under the paraxial approximation. And then we expressed the state using schemate decomposition as a separable mode pairs and derived the schemate number K as a measure of entanglement, which quantifies the number of entangled spatial modes and determine the imaging performance. So in the next, now we will see like what exactly or what actually happens when the signal photon hits the sample, and how does the phase information of the charge density transfer to the idler. Now I hand over to Vidya, who will explain the density matrix and furthermore. Thank you.
Hi, this is a project. This is a paper based on quantum diffraction imaging. This represents a paradigm shift from classical imaging by exploiting entanglement and quantum correlations. In classical diffraction, we actually measure the intensity, which is proportional to the Fourier transform of the object. This squaring process destroys the phase information, leading to the well-known phase problem. So while we are dealing with the quantum imaging leverages entangled photon pairs where one photon interacts with the object and other serves as a reference. By measuring correlations between these photons, we gain access to the information that is linear in the object's charge distribution rather than quadratic, which preserves the phase information. So as uh, Priyanka might have discussed about how up to the Smith decomposition and how the interaction with an object induces coherence between Smith modes, and how this coherence forms the basis of image reconstruction that I will take up. So, what is a reduced density matrix? The reduced density matrix is central to understanding quantum imaging because it represents the part of the system that is actually observed. In our setup, we we only detect the idler photon while the signal photon interacts with the object. Therefore, we must trace out the signal photon from the full density matrix. So, um, so mathematically, which this is written as rho I, which is trace of all the signal of the density matrix with sum or over all the possible signal states. This process converts a pure entangled state, we can say, into a mixed state that contains both probabilities and coherence information. Before the interaction with the object, the reduced mental matrix is just diagonal in the Smith basis. This means that each mode contributes independently with no interference between the modes. Physically, this corresponds to a situation where idler photon carries no spatial information about the object. Mm, coming to the interaction with an object, so we write this Hamiltonian as the charge that interacts with this is like first order interaction, we can say. So the interaction between the light and the object is described by this Hamiltonian, derived from quantum electrodynamics. This involves the square of vector potential, reflecting how electromagnetic field couples to the charge distribution. When we expand this field in a Smith basis, the interaction takes a particularly insightful form. It becomes a sum over um, some mode operations weighted by matrix elements called sigma of like sigma nm. These matrix elements represent the overlap between the object's charge distribution and pairs of spatial modes. So this is an image that I reproduced from data, which I've assumed like I produced a random shape which is in form of X and it has some thickness. So this is produced. This sigma nm matrix is produced from that information, which is in the Jupyter file attached to. This mode mixing is the origin of the coherence. So here the mode mixing happens. So this is the origin of coherence in the system. It's not the intensity that changes, but the relationship between the modes that is the change we observe. This subtle shift from intensity to coherence is what enables the quantum imaging actually. So coming to this is what I was discussing about, like um, this in the classical picture, the intensity is proportional to the uh, sigma square, but instead in quantum it's linearly dependent. Um, so coming to uh, this is the matrix after the interaction, like the after the object, the density matrix changes and the off diagonal terms will come into the picture as the coherence appears. So after the signal photon interacts with the objects, the reduced density matrix of the idler photons changes. Instead of being purely diagonal, now it contains off diagonal elements too. So these off diagonal elements represent represent coherence between different Smith modes actually. This is what they are trying to this is the key result in the paper. Like the object does not simply modify the intensity distribution of the light. Instead, it modifies the correlation between the modes in an entangled system. Before interaction, the density matrix is diagonal, meaning there is no coherence between the modes. Now, each mode behaves independently, contributing according to its weight. So this is the it has like while expanding the Smith modes, it looks like this. The matrix describes how the object couples different spatial modes, effectively mixing them and encoding the spatial information or structure into the mode interactions. Uh, Only after interaction does the situation change. Like the situation changes. The object introduces correlation between the modes, breaking the diagonal structure, and therefore the transition from diagonal to non-diagonal density matrix appears, and which is the signature of imaging. So one of the most powerful ideas in the paper is reweighing the Smith modes. Like in typical entangled source, the Smith weight decays rapidly, meaning that only a few low order modes contribute significantly. But we filter out higher order modes which contain more spatial data, like fine spatial details, we can say. These modes are essential for reconstructing sharp features of the object, but their contribution is suppressed by the small weights. Reweighing addresses this problem by artificially flattening the distribution of the weights. This increases the contribution of higher order modes, effectively enhancing the spatial resolution. I have an image. This is the reweighted image where this is just reconstructed image that the diffraction pattern. We got the signal and we we cannot see what's happening in it. This is the low weight, so like it suppresses the higher order modes. But now we filter out those modes and we can see the enhanced image of this object. This is the charge distribution that I took, that I constructed, which has some thickness and it has some quantities that which interacts with the light. And this is the picture after reweighing the reweighing, and we get the enhanced spatial detail. Uh, this process is analogous to applying high pass filter in classical imaging, but it operates at the level of quantum modes. It demonstrates that resolution is not only determined by the optics, but also by how information is distributed across modes. Mm, uh, the key insights, coming to the key insights. Mm, Actually, this this charge distribution shown here represents the object being imaged. It contains sharp edges and high frequency features which are challenging to reconstruct using only lower order modes. So the object serves as a source of the mode coupling. Its spatial structure determines the values sigma and m, which in turn determine the coherence pattern in the density matrix. Um, so what I want to conclude with is the central insight of this work is that the quantum imaging relies on coherence rather than the intensity. The object modifies the relationship between the modes, and the relationships encode both amplitude and phase information. This fundamental this is it is this fundamental concept which is different from the classical imaging, where only intensity is measured by accessing the coherence. Quantum imaging provides richer and good description, like a full detailed description of the object. So that's all. Thank you.
My name is Satyam Verma. I am going to present on this topic quantum phase sensitivity diffraction and imaging using entangled photon. So I will be going through some basic details and discussions where I will talk about the motivation. So motivation is that we have some limitations in classical diffraction. Suppose if we are doing some imaging using the classical means, then we are bounded with some parameters. So those parameters will lead us to get lesser information about the sample. So this classical diffraction measures this. SQ is a measurement parameter which is proportional to this mark sigma q square. So where sigma q is the charge density of the sample, and this q is the diffraction parameter. So in this case, actually only intensity is being measured. So phase information, we are not getting any information about that. So somehow we are losing some information about the sample. So these are the drawbacks. So to get rid about these things, the authors have proposed another way to do this kind of imaging. So that is using the quantum means, in which they are utilizing the various quantum properties like entanglement. Mainly here they are utilizing the entanglement. So consequences are we can't reconstruct the real space charge density sigma r in this classical case, since it requires the phase information, but there in classical there is, I mean, it is very hard to get the phase information of that. So it leads to the complex experimental techniques. So to avoid that, authors have proposed another way, which is more, I mean, not that much complex and easy to implement all that. So in section 4, actually, my other group members have presented the remaining sections before this section 4. So in that they would have talked about how the things are going on, how the quantum entangled source is being generated, and how these Lin numbers with mode are being calculated. So I will be not going too much detail in those. I will just start from this section 4. So where this reweighted model contributions is being described in that what they are doing, I will be going through that. So from quantum to image reconstruction. So this here we are seeing this expression. So this is an expression of two photon state described in Schmidt modes. So this lambda is a Schmidt number, Schmidt coefficient, I will say. and this UNQS and VNQI are the modes. So this UNQS represents the signal mode and VNQI represents the idler mode. So object information is encoded by via this expression, where this expression actually is the uh, coupling coefficient or coupling parameter, we can say. So the expression is like this. Then coincidence image. So image information is in this section. So SIOI directly proportional to real observation, this under root lambda and all that expression. So after that, why do we need reweighted or construction or reweighting? Why reweighting is needed? So coincidence image expression is this. So suppose if we are getting the, changing this coupling parameter beta nm, so we can write this another expression. So what is the difference between these two? So one expression is having this this term, the mostly this parameter is different. So that was actually the coupling parameter. So I will be telling in further slides that how this expression is giving more information about the sample. So observation about this. So each mode contributes with weight lambda. So distribution of lambda is non-uniform. So the higher modes, they are having lesser weight of this lambda number. So we will be not using the higher and higher modes because these weights are having lesser value. So see the information as which we are getting about the image or sample, that will be also less since it is directly proportional. And what is the problem that this higher order modes lead to the smaller weights? So that I have told. Contribution of these is suppressed the same because these modes have less weights. So contribution in that in the information, getting whatever information we are getting will be very less. So the meaning of the civic modes, what are those? So basically other group members would have explained it very well, that what is the meaning of that and all. So I will be briefly telling about this. So civic modes as spatial information channels. If we give a term to this, then we will call them like swim modes as a spatial information channel. So image is decomposed into orthogonal spatial modes. So we have seen the expression which like coupling parameter and this S parameter, which is the actual information of the sample. In that actually these modes were present. So these are being known as the split modes. So a distinct spatial feature of the object, projection of the charge density. These are the main work of this mode. So what they do actually, they do this a distinct spatial feature of the object, and they also project the charge density. And then the expression I have shown previously in this slide, this expression. So here this first order coupling parameter, then second order coupling parameter. So in first order actually we are not losing any phase information, but here we are taking the mod square. So here we are losing the phase information. So what are the outcome of this? So higher order leads to rapid spatial variation and the fine spatial details. So that's why we use the higher and higher order modes. So truncated mode reconstruction. So this expression I have shown previously too. So here this lambda is symmetric weights and V and rho is spatial modes. So also symmetric modes V and beta PNM is a scattering coefficient or coupling coefficient between split modes and has no classical counterparts. Sorry. And the limitation. So natural spectrum mode weights lambda are not uniform, decays rapidly with the higher index Nm. So what we do? So we take the, we do this reweighted construction. So effect of reconstruction in this low order modes dominate and higher order modes negligible contribution. So now I will discuss about the Hermite Gaussian modes, how they are being represented. So this is the expression where Hn is the Hermite polynomials, and the modes are shown in the next slide. So here I have shown the modes, how this 0, and then 0, 1, 0, 2, 0, 3, all these modes are being shown. So this is a visual representation of the Smith modes in Hermite Gaussian beam. And now I have reconstructed and simulated some images of the given in the paper. So these images are taken from the actual paper. So in this first plot, they are plotting the Smith weights of entangled light source. So in this axis, the front axis, this representing M, and this side axis representing M. So these are two modes of we can say of sigma and idler. So then on this vertical axis, this represents the Smith weights. So here they have reconstructed the images. So the upper row is uh, the image where they are taking the normal weights. They are not taking any re-weighted construction. So here they are taking 5 modes, n equal to 12 modes, and n equal to 20 modes. And then second row, they are taking the mode number same, but they have used that technique, the re-weighted reconstruction. So we can see that they are getting a more finer detail about the object. So see there n equal to 12 upper row plot or figure, and then n equal to 12 the lower row plot. So here there is a clear distinction that they are getting more information about the object. So this is the speciality of the reweighted constructs where we get the more information about the object. So this simulation I have done. So here this on the vertical axis the same Smith weights, and this n and m are the mode numbers. And these images, there are some distinct kind of objects. So here also the same n equal to 5 modes, 12 modes, 20 modes. Upper row shows the natural weights, and the lower row shows the uh, reweighted construction. So we can see the clear distinction. In this actually it is not that visible, but we can see even some more clarity about some tiny details. And then some other simulation using the same thing. So here it is more visible. So upper row with original weights and the bottom row with reweighted construction, where actually we are getting more information. See, here it was more blurry, but here we are getting some extra information too. So here actually this side plots are showing the real part with phase and then phase recovered, but this was not possible in classical case. So this is the speciality why they are using quantum entangled photons. Then final discussion and conclusion. So overall imaging framework is in such way that first we generate the entangled photon source file. Then we get to know that about the spectrum modes and how spectrum decomposition is being done. This expression is here. And then interaction with the object. So this was the coupling or interaction parameter we can say. Scattering parameter 2. Then image formation. So this was the parameter for which we form the image. So key result of this presentation are quantum diffraction enables access to the phase information, which is not possible in classical case. Then signal scaling is like signal directly proportional to root of intensity, square root of intensity, and coincidence counts are intensity to the power of 3 by 2. So this enables low intensity imaging, but in classical case, it was not like that. So in classical, signal strength was proportional to the IP, and coincidence was some root I think. So resolution depends on entanglement, spatial correlation between photons. This entanglement actually is the property of that signal idler. So resolution depends on entanglement. So if photons are highly entangled, so we'll be getting the better and better resolution about the sample. So reweighting enhances the contribution of higher order spatial modes to get more information. So this is the main thing which reweighted construction tells us. So thank you all. And